All right, let's walk through the calculations here for homework number 2. This is an assignment on assessing the effect of force, magnitude, and direction on performance in vertical jumping for maximum height. So we have here an athlete who is trying to jump as high as they can, and we have their body mass in kilos. We have the magnitude of their ground reaction force in newtons. We have the direction of that ground reaction force in degrees. And we have their ground contact time, the amount of time their feet were on the ground producing that force. Okay. Magnitude here, this is just how big is the ground reaction force. And direction, that's, as you should guess from the name, the direction of the ground reaction force. That is the angle of that force vector relative to the right horizontal. So if this angle had a value of 0, that would indicate that it points straight horizontally and has no vertical component at all. If it had, at the other extreme, if it had an angle of 90 degrees, that would indicate that it points straight up and down and has no horizontal component whatsoever. And the prompt here will walk you through interpreting that. And if you want it to be horizontal versus wanting it to be vertical or some intermediate value here. Purpose of this video is let's step through the calculations involved here. Okay. So what we want to do is, from these numbers, we first want to determine how high did this person jump when they jumped with this particular force in this particular direction here. And we then want to assess the effect of changing the direction of that force and how much higher we jump there. So how do we do that exactly? I'm going to pull up a spreadsheet here. I'm going to close my old one. Pull up a spreadsheet here. And I'm going to first copy over these numbers that I've already got. Mass in kilos, 75. GRF magnitude, I'm just going to call that GRF. It's 1,000 newtons. GRF direction, I'm going to call that Q, degrees, 75. And contact time, I'm going to call that T, seconds, 0.9. Okay. I'm also going to need gravity here, meters per second squared, and that's 981. Okay. First thing that I want to do here is this force, 1,000 newtons, is directed at this angle, 75 degrees, relative to the right horizontal. So if I'm jumping for maximum height, only some fraction of that 1,000 newtons is pointed in the vertical direction and is causing me to jump vertically. The rest is directed horizontally and is not moving me or changing my momentum in the vertical direction. So first thing I want to do is I want to figure out what is the vertical component, GRFY, of the ground reaction force. Okay, and that's going to be the overall force magnitude times the sine of that angle there. And sine expects my angle to be in radians, so I'm going to multiply those degrees by pi over 180. Okay, and that gets me the fraction of that ground reaction force that's directed in the vertical direction. Okay. Now, this person has a certain body weight that they have to overcome to jump. So it's the amount of this vertical ground reaction force above and beyond my body weight that's going to cause me to lift off the ground and go upwards off the ground. You can also think of this as, if I'm standing still, then gravity's pulling me down with my body weight. My feet are pushing me up against gravity, also equal and opposite to my body weight. So that's when I just stand still and don't go anywhere. To actually move upwards against gravity, I have to produce a force above and beyond my body weight. So to get the force, I'll call it Fy here in newtons, above and beyond my body weight that's going to cause me to move upwards against gravity, I'm going to take this vertical ground reaction force and subtract from it my mass times gravity. And what's left over there is my net force in the vertical direction that's going to cause me to jump vertically. Okay. And from that net force, I then, using the impulse momentum relationship, want to figure out my takeoff velocity. And impulse momentum, if you think back to Knies 300, that was impulse, force times time equals mass times velocity. And here I have everything I need to calculate velocity. I've got my force, that's Fy. I've got the time that force is applied, t. I've got my mass, m. So the only thing I don't know in this equation is v. I can solve for v. Take the force times the time, divide by the m, and that gets you your v. So my takeoff velocity is going to be net vertical force, F, times time, t, divided by mass, m. Gets me a takeoff velocity of about 2.7 meters per second. And then if I use my equations of projectile motion, my height that I jump to in meters, that calculation was velocity squared divided by 2 times gravity. That gets me my height in meters that I got above the ground when I left the ground. Metric system is what we use in science. 0.38, 0.39 meters. Usually we have an easier time thinking about inches. Like a 40-inch vertical jump. That's a really good vertical jump. A 20-inch vertical jump for like a average person. That's pretty good. Most of us probably can't jump 40 inches unless we're a really good athlete. So let's convert this height to inches to get it in units that we have a little bit easier time assessing and a little bit more familiar with. So take my meters, multiply by 100 to get it to centimeters, and then there's 2.54 centimeters in an inch, so divide by 2.54, and that gets me my height in inches, about 15 inches of a jump there. Okay, so that walked me through doing the calculation here to figure out how high did I jump when my ground reaction force of 1,000 newtons was pointed at an angle of 75 degrees relative to the ground. Okay. The first task that this homework asks you to do is to then repeat that calculation. If I then improve my technique such that now that 1,000 newtons is pointed perfectly vertically, it's pointed upward at an angle of 90 degrees instead of kind of upward at an angle of 75 degrees. Okay. Nice part about having this all laid out here is now I can just go into my angle and change it from 75 to 90. And watch what happens here when I do that. Now it just automatically recalculates everything and I got my new height there. Okay. So changing my angle from 75 degrees, where it got to jump about 15 inches, to 90 degrees. Now I get a jump of about 20 inches, right? So I got about a 5%, or sorry, about a 5-inch increase in jump height by improving my technique there. That's pretty good. 5 inches is a quite a good increase in jump, especially when I'm only starting out at 15 there. Okay, another calculation it'll ask you to make here is, suppose I left this at 75 degrees, and now I'm back to jumping only 15 inches. How much would I have to increase my strength, reflected here by an increase in my vertical ground reaction force that I can produce, to jump that high to go from 15 to about 20 inches? How much bigger do I have to make my ground reaction force here to get that much of an increase in jump height? Right? So then you can play around with it. If I decrease this to 900, then I jump quite a bit lower. If I increase it to 2,000, then I jump 413 inches in the air, some impossible jump height there. So play around with that number and see how big you have to get it, or see how much you have to increase it by to get about that same increase, up about that same plus 5 inches there when you leave it at 75 degrees as the angle rather than changing it to the 90 degrees there. All right, so it can give you kind of an assessment of improving my technique here from 75 degrees to 90 degrees, and there I got about a 5 inch increase there in jump height. How much, like what's the like increase in strength there? Are we talking like a 1%, 2%, 10%, 5? How much does my strength have to increase, reflected by a greater ground reaction force there to get that same increase in jump height if I didn't improve my technique at all, and if I just keep my strength there. Another assessment I'll ask you to make here is, you'll see that you can increase this ground reaction force to increase the jump height here, but that's reflected by an increase in like muscular strength. And is it realistic to think that I'm increasing my muscular strength without increasing my muscle mass there, my body mass? Generally, if you get stronger, you're also a lot of times also going to get a little bit heavier, right? So is it realistic to increase my strength without increasing my mass at all? Maybe, maybe not. And if I increase, say, my strength by 4%, and from a 4% increase in my body mass, then do I still get an increase in jump height? And this will hopefully that's intended to demonstrate for you that jumping is really about like pound for pound strength and power. It's not enough to just be strong and powerful in an absolute sense to jump high. You have to be strong and powerful relative to your body mass. It's the person that's pound for pound strong that's typically the best jumper, not somebody that's just strong in an absolute sense. Okay, that should help you out with the calculations there for homework number 2.